efficient reductions for k nearest neighbor search, or I guess how to fry the binary strings.
Yes. Okay. Great. So, thank you very much. Thanks for staying here until the end. So this is I'm going to talk about joint work with Tobias Christiani, who is here, and Mikkel Thorup in Copenhagen. And yeah, to make everything self-contained, let me just start by defining the problem. So we have a point set P consisting of points x1 through nn in some space, and we're interested in pre-processing this point set in such a way that, given a query q, we can efficiently find the point that is closest according to some notion of this distance of the space. So let's denote nn of q. So this is the main problem I'm going to be talking about. A lot of work in this area actually deals with a slightly different problem. So Alex was also mentioning it. So that's the near neighbor search problem. So you're given not just the query point, but also a particular radius r. So this might be given even before you start pre-processing the data set. And the problem from the slide, the k nearest neighbor search is just the generalization of the nearest neighbor search, where you want to report not one near point, but k near points. Okay, so I'm going to focus on k equals to 1, but basically all of the things that I'm going to tell you generalize to the case where k is large. So this is a problem with a lot of applications. So you can find applications basically all over computer science. I'm not going to go too much into that. Unfortunately, it's not a problem that we can hope to solve extremely well, not like other kinds of search problems. And as Alex mentioned, this is because we have hardness. Okay, so there are different ways of formulating this hardness, but here's one of my favorites. So it's due to Williams, and I think developed a little bit more by Allman and Williams a couple of years back. So we're looking at a very simple space. So we're just looking at the Hamming cube in d dimensions, and suppose we're able to do near neighbor search in just slightly sublinear time. So just n to say 0.99, okay, and time that is also sub-exponential indeed. So this is kind of the least we could ask for, basically. So this is just slightly non-trivial. So it beats linear search. It beats kind of enumerating all the answers. Okay, and suppose we could do this with pre-processing time that's polynomial in n and sub-exponential indeed. So if that was possible, it would have a surprising consequence, namely that k-sat could be solved fast. And fast here would be c to the n for some c smaller than 2. Okay? This is a famous problem in exact algorithms, and there's a conjecture, the strong exponential time hypothesis, which says that this is not possible, probably not possible. So at least under this conjecture, we cannot hope to do anything really non-trivial. Okay? Or you could turn around and say, if we actually do something non-trivial, then we'll make progress in exponential time algorithms. Okay. So this is not just a theoretical thing. So in practice also, people refer to something called the curse of dimensionality, which means that if you try to solve exact nearest neighbors, maybe using some kind of search tree or something like this, it becomes very slow in high dimensions. So also in practice for practical data sets. So you quickly degrade to something that is basically as slow as linear search. All right. So this is hard. So what can you do to address this? Well, you can look at approximate nearest neighbor. So this paper is almost 20 years old now, by Indiga and Modwani, that started this line of study. Okay, so what is the idea here? Suppose that the nearest neighbor is at distance r. Then we allow a little bit of slack, so we actually consider a larger ball of radius cr, and any point within this larger ball is a valid answer. Okay, so this is C approximate nearest neighbor, and the point is, like Alex also said, in this setting, as soon as C is larger than 1, then you can get sublinear query time, and to the row of C, where row of C is some number less than 1 that depends on C. Yeah. And there's been a lot of work trying to get the best possible row values for different spaces, but I'm not going to go into that. So in practice, okay, so this is a screenshot from a site called NN Benchmarks. So it shows all kinds of algorithms for nearest neighbor search algorithms. Okay, so they also call it approximate nearest neighbor, but what they mean is actually something pretty different. Okay, so here on the y-axis is the speed. So the higher up, the faster. And on the x-axis is a notion of how precise it is. But it's not about approximation factors, it's about something called recall. So recall is just the fraction of nearest neighbors that you find for a particular set of queries. Okay? So these benchmarks have a predefined set of queries where you run all the algorithms and you see how many of these queries actually find the nearest neighbor. Okay? And this gives you a fraction between 0 and 1. And you can see that the higher fraction you want, the slower the algorithm gets. None of these methods, except maybe if you want to get everything exact, so if you want to be here or here, something like this, then there's a guarantee. But otherwise, all of these points are really just empirical. Okay, so there are no real guarantee that you are going to achieve this kind of recall on a new data set. Okay, so there is kind of this discrepancy. So we have theoretical work that has approximation in terms of distance approximation, and we have these empirical results that talk about kind of the fraction of time we succeed in practice.
Is there any curve here which is like a trivial algorithm that just says, just look through all the points, just to understand where it would be on the scale?
Yes, I think this point down here on the bottom right is not trivial, but it's some kind of search tree that guarantees to find the nearest neighbor, as far as I recall. I don't think brute force is on there, actually.
Mm-hmm. But there's brute force plus.
Sorry?
There's a brute force plus.
Okay, yeah, maybe that one.
Off the chart, though.
It's it's hard to see here. So go to ann.benchmarks.com. You can inspect all of these. It's a really nice site. So you can there are all kinds of nice visualizations.
So just can you tell us, are there any of our favorite theoretical algorithms in the mix that you can point out?
Here, okay, so until recently I think there was one library called FALCONN that was on there. So I think right now it's not on there, is that right, Ilya?
Yeah, that's right.
Yeah, but I think it'll probably appear at some point in the future. Well, you can ask Ilya about it, and we are also my group is also working on implementation, so we're hoping to add there. But right now, I mean there is stuff based on theoretical work, but it's not kind of state of the art. All right. So what we would really like is to also say something in theory about recall. Okay, and one attempt might be a black box reduction. So suppose we just choose the approximation factor small enough, then of course the approximate nearest neighbor would actually be the nearest neighbor. So that's one attempt. But I mean this doesn't seem to be the right way, because it doesn't really distinguish between easy and hard cases. So for example, here on the left, the nearest neighbor has almost the same distance as the second nearest neighbor. So we would need an approximation factor very close to 1. The same is true on the right-hand side, but that instance actually looks much harder, because there are lots of points that have almost the same distance from the query point. Okay. So just having a black box reduction doesn't seem to give the right answer in the case on the left. Okay. So what you can do, and what people have also observed that you can do, is that you can kind of unpack this black box and look at some of the methods that are actually used. And for example, one could do this with LSH, with multiprobing. So I'm not going to even, I mean, I can explain in a few minutes what it is, but I'm actually just going to treat it as an abstract black box. So it's some linear space data structure. It's basically some kind of hash table that allows us to retrieve data points with different probabilities. So xi is retrieved with probability pi, and the idea is that closer points are retrieved with higher probability. Okay. And let's just say that the nearest neighbor is x1, such that p1 is the probability that we retrieve x1. Right. So we can query this data structure, and it has an expected cost that depends on some parameters. So there are some internal parameters that you need to specify called k and t. And then of course you have to look at all the points that you have retrieved. So the cost is at least the sum of the probabilities, so the expected number of points that you retrieve. All right, and now I won't really go into how you choose these parameters, but you somehow choose them to optimize the running time in the end. Now, suppose you have this. What is the probability that you fail? Well, it's pretty large. It's 1 minus p1. But you can of course repeat. Okay, so suppose we repeat independently L times, capital L times. What is the probability that we fail? Well, it's the probability that we fail each time. So it's 1 minus p to the L. And so if L is large enough, so it needs to be something like log 1 over delta over p1, then we have probability 1 minus delta of succeeding, actually finding the nearest neighbor. Okay, so in other words, we get, with this number of repetitions, we get expected recall 1 minus delta. Of course, we don't really know in advance what P1 is, so I'm going to come back to that. But there's also this annoying issue of these parameters, right? And this is actually something that people, worry about in practice. They have some data sets. They need to set these parameters. So what do? They go to the documentation of the software they're using. Maybe they go to the FALCONN documentation. So yeah, so this is Ilya and Ludwig who implemented, I think, everything or most of the library at least. Okay, and it has some advice about choosing parameters. So it's down here, and it kind of says you need to do a parameter search. You kind of try increasing values, and then for each value you try other values and so on. So it's really, it's really an empirical task. So you have to look at a particular data set, maybe query distribution, to choose these parameters in a good way. Of course, theoretically, you might say, okay, there's just polylog different parameter choices. Maybe we can kind of try them all in parallel or something like this. But in practice, any polylog factor is going to kill whatever speed up we get from the approximation. Okay, so we would like to do something better. Okay, so something that adapts to the data and also to the query. So if we have a query that is really easy, maybe the query is very close to one of the data points, we should be able to find that data point quickly. If the query is quite far from most data points, we'll have to spend more time finding the nearest neighbor. Right. So one such technique, and this is only something that I discovered recently, was described 10 years ago by Dong et al. So it's in a kind of in an applied conference. But there is this section that describes something called adaptive stopping. Okay, so suppose that we are searching one of these hash tables, for example, using multiprobe LSH. So we are searching one hash table after the other. Suppose we have searched T hash tables, and the nearest point we saw so far is X star. Okay. So we would like to know if we can stop. Is it likely that X star is actually already the nearest neighbor. Right? So let's suppose we can actually compute the probability of finding x star in a particular hash table. Okay. It's non-trivial how to do this, but let's suppose that we can get this probability, and let's call that p star. Then it turns out that if t is somewhat bigger than 1 over p star, so if t is so large that you would have expected to see x star log 1 over delta times, then we can actually stop and return x. And with probability 1 minus delta x or x star will actually be the nearest neighbor. So if you think about it for a little while, it's pretty easy to see that this is the case. So why is this not quite ideal? Well, it requires us to compute or estimate this quantity p star. Okay, and depending on the kind of method we use for multiprobe LSH, this can actually be pretty difficult. Okay. So let's step back. So what I'm going to present is kind of a simpler alternative that is essentially as good. So let's just step back and take a slightly more abstract view. Okay. So the query algorithm from the beginning, we just know the query. And now what we can do is that we can inspect one of the hash tables. So actually what is going to happen is that there is some part of the space. I've drawn it here just as a rectangle. And we're going to look at all the points from the point set that are in this part of the space. Okay? And one of the points is going to be closest. Let's suppose it's this one, beta. Okay? Then we go to the next hash table. We look at a different part of the space. Maybe there's a closer point in there. And we go on like this. Sometimes we don't find a closer point. Sometimes we do. And we continue like this for a while. And now we would like to understand, can we stop? How can we know if beta, the current closest point, is likely to be the nearest neighbor?
So just to make sure I understand, so each of these times what you're doing is you're looking at all the things in the same bucket and then looking at the closest number. Yes. That's how you get one of these points. Yes,
so look in a bucket, the closest one is kind of the candidate from that bucket. And you see if it improves the previous one. Yes, that's right. All right, and if you look at this picture, it kind of looks like we should be pretty safe, right? Because we kind of looked everywhere inside this ball, it seems. But in general, what does it take to be pretty sure that what we have found so far is actually the nearest neighbor? Okay, so we explored this idea of confirmation sampling. So the idea is that, so in each repetition we get some candidate, which is the closest point in the bucket, number I. So let's call that yi. And we do this independently for each I. And let beta I be the nearest neighbor found in the first I steps. Okay. So now the stopping rule is that if in repetition I we see copy number t plus 1 of the current best nearest neighbor. So in other words, if beta I appears t plus 1 times in the candidate set so far, we stop. Okay, so t here is just a parameter. So in other words, so we get a nearest neighbor candidate beta. We see it for the first time, and then we see it t more times without seeing anything that is closer. Okay. Then we say that this nearest neighbor candidate is confirmed t times. So when Tobias told me about this idea for the first time, I actually thought that it probably didn't work until we realized that it did. So the claim is that the nearest, at least if we assume that the nearest neighbor is more likely to be a candidate than anything else. Okay, So the probability that the best thing from a hash table that we look at is the nearest neighbor is at least as high as any other data point. Question?
Isn't it safer to actually say that a particular distance appears t+1 times in case there are multiple points that are almost nearest neighbors, because each of them might appear and sort of screw this rule up?
Yeah, like how does it work if you have 2 points with the same probability?
Yeah.
Okay. Yeah, I mean 2 points with the same probability or the same distance is fine. You just need a tie-breaking rule.
But if they're absolute
But almost the same.
Almost the same is fine. Almost the same is fine.
If the distance is the same, then you go with T.
And actually,
No, but if it's almost
it only needs to be the most likely up to a constant factor. So it's actually fine that there's some other points that are 10 times more likely, just as long as it's bounded by a constant. All right. Okay, so let's go back to the previous example. So we have our query. Let's do confirmation sampling with t equals to 1. We get a sample. So this is the best seen so far, of course. We set it equal to beta. We get a new sample, which is slightly better. Update beta, get another sample. We don't update beta, get another sample, update, and so on. Actually, okay, so now we actually found the nearest neighbor, as you can see, but we don't know that, so we continue for a while until we see the nearest neighbor once more. And that's our confirmation, and we return beta. So, very simple method. Okay, so why does this work? So suppose x1 is the nearest neighbor.
So can you
Yeah.
repeat the claim again? What you're trying to prove?
Okay, so I'm trying to, I want to argue that the probability that we return something other than the nearest neighbor is 2 to the minus t.
So either you mean either a specific point or any, like union of all other points?
Any other. That we return something wrong is 2 to the minus t at most. So what does it take to return something other than the nearest neighbor? It requires something called false confirmations. So it requires that at some point, the best thing we have seen so far is beta I minus 1, and we see it again. Okay? So beta I minus 1 is the best so far, and then we sample the same point once more in the ith hash table. But it's not the nearest neighbor. Okay? So we call that a false confirmation. And the essential thing to observe is that all that matters are steps where we see either the nearest neighbor or a false confirmation. Okay? So if we sample something that is different from the current candidate beta, it doesn't matter. So these are the only things we care about. So let's see. So let's consider the first t steps where we either sample the nearest neighbor or produce a false confirmation. Okay. So I mean, so this is the gist of the idea. So it needs a little bit more work to be made completely formal. Okay. But essentially, because sampling x1 is more likely than sampling this beta I minus 1, the probability, given that you know that you either see x1 or get a false confirmation, the probability that you get a false confirmation is at most 1/2. And this needs to happen t times. Okay? So all in all, the probability of getting t false confirmations and returning something wrong is at most t 2 to the minus t.
And to make it more formal, you're saying you don't need to lose any more constants?
No, we don't lose any constants. Yeah. To make it more formal, you need to split the probability space into, cases where these confirmations happens. I mean, which steps these confirmations happen, and so on. But in each of these cases, you can do this analysis. Mm-hmm. All right. So this actually is an abstract algorithm. So you can write up like this abstractly. So we have some way of sampling from a space, and we're looking for the smallest element from the support, basically here according to some order. If we sample something that is equal to the smallest element seen so far, we increase our counter. If we sample something that is smaller than the smallest thing seen so far, we update the candidate and set the counter to 0. And we continue this until we have a count of t. Okay. So it turns out actually, as I was mentioning before, that this works even if what we're looking for doesn't have the highest probability of being sampled. Okay, as long as the highest probability is at no more than a constant factor higher than the probability p1 of sampling what we're looking for, we get exponential decay in t of the failure probability.
So, and one of the things in LSH is you also want to control the number of other points getting into the bucket.
Yes.
If you are taking too many buckets.
Right. I mean, I kind of push that issue aside for now. Yeah, but we'll get back to that. Okay. How long does this take? Well, I mean, the latest time that we are going to terminate is the time when we have sampled x1 t plus 1 times. Okay. Maybe we get false confirmations and we terminate earlier, but no later than the time we sample x1 t plus 1 times. We return, and this happens after t plus 1 over p1 steps in expectation. And this is actually, even just to see x1 with probability 1 minus 2 to the minus t requires roughly this number of steps. So we couldn't really hope to get a much smaller number of samples. So it's optimal with respect to the number of samples just to see the nearest neighbor up to a constant factor. So we can apply this to nearest neighbor. And now I'm just assuming that I have these data structures that each of them gives us the nearest neighbor with some probability, and they give us other points with some probability that is not larger than the nearest neighbor. And so it's assuming that someone gives us this sequence of data structures, then we can query the optimal number of such data structures depending on P1 without actually knowing P1. So the number of data structures that we're going to query is log 1 over delta divided by P1. So what does this mean? It means that if we want to find the nearest neighbor, it basically boils down to constructing these data structures such that the product of the time and 1 over P1 is minimized. Okay. Maybe you can think about these data structures as having a time budget also. How much time do I allow them to spend? And given this time budget, they need to maximize the probability of actually finding the nearest neighbor. And one question here that I'm not going to answer today is whether you can construct these data structures optimally without actually knowing the distance to the nearest neighbor. So most of the literature on this problem assumes that you have a particular radius that you're interested in searching, and that simplifies a lot of things. So what we did do, so though we didn't find an answer to this general question, we did find a partial answer for a particular LSH data structure called the LSH forest, which is it's a sequence of space partitioning. So each tree here in this forest is a recursive space partitioning. So you get space partitionings at many levels of granularity. The further down in the tree you go, the more fine-grained partitioning you have. And for a particular query, if you have, say you have a query that is far from most of the data points, then a very coarse partitioning is enough to actually not have to look at too many data points. If you if you have a query that is quite close to a lot of data points, you might need to have a more fine-grained partitioning. Okay, so, and the standard query algorithm for LSH forest is that you search a level of these trees where the average number of points you see in a partition is constant. So this is how you usually search LSH forest. And this, you can show that this works if the number of trees is high enough. Okay. But high enough actually depends on the distance to the nearest neighbor. So it's not quite, I mean, even though it claims to be kind of adaptive to the particular query, I mean, it does need to make some assumptions about the distance to the nearest neighbor. So what we can do instead is to modify the query algorithm such that it actually also doesn't just search this level where the number of points is constant on average, but also searches higher levels until confirmation sampling tells us that we can stop. And we may also need to, it turns out that we also need to consider partially searching a level. So not searching all the trees in a level, but just searching a prefix of the trees to get the best results. And kind of roughly speaking, what we can show is that if we do this, then we are competitive, at least with the best way of searching an LSH forest for the given query. So, okay, so even if we had kind of known ahead of time what the position of the query was with respect to the whole data set, and we could choose the optimal level and the optimal number of trees based on that, we can get within like a constant factor in time and space from that performance. All right. So I think the main open question that we have is really whether we can find kind of an ideal adaptive data structure to work with confirmation sampling. So ideally what we want is a method that is competitive with the best LSH scheme that is tailored to both the query and the data distribution.
So can I ask a question about the confirmation sampling?
Sure.
If in order for the result to work, where you see the nearest neighbor multiple times, does that need to be over the same family of hash functions, or can you adaptively change that?
No, so actually everything works even if you have a new, if you sample from a new distribution every time, as long as you can bound the probabilities. So you could in principle, use different kinds of hash functions if you wanted to. And the hope would be that one could get kind of the optimal probability of returning the actual nearest neighbor, or in other words, instead of just looking at recall as an empirical thing, one could try to prove theoretical results for expected recall. All right. So that's all. Thank you very much.
Questions?
So here everything was parameterized by the P1 and P2, like the, and of course you pay for the fact that you look at the bucket and then you need to find the closest element in the bucket.
Right.
And yeah, I don't know how in practice if this is something that has high cost or not, but could you see the analysis extended where you have the full PIs and then under some structure, like all the PIs, and under some structural assumption on the data set, you can prove that this quantity is small?
I'm not sure I got the question.
Let's say that you're only allowed to look at a certain number of points in its bucket. You don't want to spend that time to scan the whole bucket. Yeah, so something that could also, because right now, if you have a very large bucket, this result still holds, but it might, you have linear, you could do, have linear time of, So.
Yes, but I think that's, given the hardness results, that's probably unavoidable. If you have like a cluster of points that are very close to each other, then I don't think there's any way to actually find the nearest point among those points in less than linear time.
No, I agree on that. All I'm asking is whether you can extend the analysis with having some PI-dependent bound that takes into account the whole data set, that in the worst case, of course, will be very bad.
We have that. Yeah, we have exactly that.
Yes, you can combine this with kind of LSH schemes and write, give performance bounds that depend on the distance distribution, basically. So maybe maybe that's what you're asking. Yes, that's right.
Just some thought on because you mentioned that the hard case is if there is a point which is close by, but if you think from a statistical perspective, every collision is kind of estimating the that P star, right? So if you have a data, then you can actually estimate you will be, over a long run, you will actually be estimating the frequency of how many times they are getting.
I think certainly if you allow a log factor overhead, you can estimate P star very efficient, very precisely. Right. So the thing that surprised me at least was that you don't need this logarithmic overhead of approximating collision probability, but you can actually do something that is optimal within constant factors and also simpler.
Yeah, what I was saying is that you can actually also a question on the data distribution. You can actually get what the data distribution looks like by seeing what all you have got how many times. So this one is fine, you look at the confirmation and then you retrieve the near neighbor, but by the time you have reached the confirmation, you will, if there are very close by points, then you will also be having a very good estimate for those guys also.
Yeah.
So there must be a way to say how much time you take is also dependent on the data. There is a way to maybe characterize the data distribution with.
Yeah, so I guess the data distribution mainly comes in with respect to the amount of time it actually takes to produce the samples. Right. So if there's a lot of points that are almost the same distance as the nearest neighbor, then it's going to be more expensive to produce the samples.
Yeah, because you get T counts for this, you might be getting T-1 for others. So
right, but yes, but we only fail if we get T confirmations before seeing something that is better. So that's.
So T may not be the factor. It may be how many distance computations you do. So you may get a lot of elements in one bucket because they are more or less similar. So.
Right. So we didn't. I didn't. But that's right. So there is a cost in terms of the number of distance computations as well.
Do you say you could extend this to k-nearest neighbor?
Yes. So for k-nearest neighbors, there are different ways of doing it. So I think the simplest one is basically to say that you need to have all of them, seen all of them T-1 times in the top K. I think that can probably be improved a little bit, but that's that's essentially it.
Let's thank Rasmus again.